In working through our Taylor series approximations, we have shown that oscillating buildings can be modeled as simple pendulums for small oscillations. We then verified this model, but we only verified this model in theory. The next step in the engineering analysis is to demonstrate that this model accurately corresponds to actual behavior. To do this, we've designed a simple experiment, and we'll perform this experiment in this video. We will then use the data from this experiment in your upcoming recitation class to confirm that our approximation is sufficient. Before we begin, I will introduce the various components of the experimental setup, so that you may note any shortcomings or assumptions that might alter our results. The structure we are measuring is a scale model of a building. In particular, this model is scaled to be the same height and footprint of the University of Texas clock tower. We are interested in observing the building as it oscillates. To start the oscillations, we will strike the building with a brief impulse, accomplished with this golf ball and string. The oscillations are measured with sensors that are attached to the top of the building. There are 6 sensors in total, 3 accelerometers, which measure rates of acceleration from 3 perpendicular axes, and 3 gyroscopes, which measure rates of rotation about these axes. The output of these sensors will provide us with all the information that we need to determine how the building is oscillating. This information is passed to a microcontroller, and this microcontroller communicates with a PC via a USB cable. Finally, the building is clamped to the table using standard C-clamps. The experiment is very straightforward. We raise the golf ball and note the angle it makes with the vertical using the attached protractor. When the golf ball strikes the building, the sensors immediately begin sending data to the PC. An Excel plugin is used to process the instructions from the microcontroller. The data is then gathered into columns, and the points are plotted in real time using an Excel graph. This is a sample data set that is very similar to the data you'll be using in your recitation class. Now, for this module, we're focused on using the Taylor series approximation of a simple pendulum to determine the spring constant of a scale model building. Luckily, most of the work is done automatically in the spreadsheet. To begin, the real-time data is somewhat noisy. Obviously, our building is not oscillating up to 20 degrees from equilibrium. So before continuing, this data must be filtered before we can draw any accurate conclusions. Again, this filtering process is done automatically in the spreadsheet. The filtered data shows us that the max oscillations are under 2 degrees, and that most of our motion occurs between plus or minus half a degree. This seems much more reasonable. We are interested in the harmonic motion of the building. This means we are looking for the data that most closely resembles a pure sinusoid, as indicated here. And once we have identified this harmonic motion, we regraph that specific data to zoom in. Looking at our zoomed in graph, even though our data is filtered, it's still too noisy to successfully take derivatives. The practical approach, and the one often used in industry, is to fit a sinusoid to our data, and then to take the successive derivatives of that sinusoid. In this graph, you can see that we've graphed the pure sinusoid in red over top of our data set. Now, it doesn't match up perfectly, but it does match up well enough for what we're trying to accomplish. In recitation, you'll have the ability to change the frequency, amplitude, and phase offset of the sine wave to accurately overlap the data set. The sine wave describes the position of the building as a function of time. You will be required to take 2 derivatives of this function to determine the acceleration as a function of time. And, according to our simple pendulum model, if we divide acceleration by position, we can then determine the spring constant of the system. The final step is to verify that the spring constant is in fact constant. If we make a scatter plot of the spring constant versus the position of the building, we should get roughly a straight line as shown. Note that the outliers are due to rounding errors in Excel. By approximating an arbitrary potential energy function with its Taylor series expansion, we were able to make the claim that any structure, no matter how complicated, can be modeled as a simple pendulum for small oscillations. We have just verified this claim by performing an experiment on a scale model building and analyzing the data from that experiment. We should note that being able to determine the spring constant of complex structures is a very powerful result in engineering analysis. Taylor series approximations allow engineers to approach this analysis in a straightforward and simple manner. And because of these models, these engineers are able to develop optimal solutions to these complex problems.